Having established the two key concepts of linear independence and spanning sequences, we're going to now put them together to form the idea of a basis. So here's the definition. A basis of a vector space V is a linearly independent spanning sequence. So that means a basis is a two-part definition. Number one, you've got to be linearly independent, and number two, you must be a spanning sequence. Let's take a look at a couple of examples of bases which we've actually seen already. So first of all, we'll take V to be R squared, and then we know that if we let E1 be 1, 0 and E2 be 0, 1, then those things are a basis of V. We've actually checked, as part of the examples we've been doing so far, that those things are linearly independent and that those things are a spanning sequence for R squared. Actually, we did C squared, but the argument is precisely the same. So those things are a basis for R squared. But we also did another example with the same vector space. So if I take F1 to be 1, 1 and F2 to be 1 minus 1, then again we checked that those things were linearly independent, and we also checked that those things were a spanning sequence for R squared. So those are also a basis for R squared. So what I'm saying here is that these are both bases for R squared. So that's an important point. The same vector space may have many different vector spaces, many different bases. In fact, a non-trivial vector space will have infinitely many different bases. Basis is such an important concept that we're going to look for several examples. So here are some more which come under the heading standard bases. So first of all, in R to the n or C to the m, we have standard bases consisting of the vectors e1 up to en, where ei is the vector which has a 1 in position I and 0 everywhere else. So that's called the ith standard basis vector, and this is called the standard basis. So let's look at what that would look like, for example, in the case n equals 3. Then you would have E1 being 1, 0, 0, and E2 being 0, 1, 0, and E3 being 0, 0, 1. So this is a basis we've seen before in the n equals 2 case on the previous slide. So this notation is so common that we're going to use it without explanation and further in future. Whenever we talk about EI, it'll always refer to one of these standard basis vectors. So let's see why this thing is a basis. If I claim that it's a basis, I've got to show you that it is linearly independent and that it is a spanning set. So these things are linearly independent. Well, let's just look at the case n equals 3, where I've written out the vectors explicitly here. So it's actually very, very easy to show these are linearly independent, because if you have a E1 plus B E2 plus C E3 equal to the 0 vector, then the vector on the left is the vector with entries A, B, C. So if that's equal to the 0 vector, so we must have A and B and C are equal to 0. That proves that these three vectors are linearly independent. And in fact, the same argument would work no matter what n was. This argument would prove that no matter what n was, the vectors e1 up to en are linearly independent. So they satisfy the first part of being a basis, but also it's really easy to see that they're a spanning set as well, because if you have a vector, so x, y, z, and let's just think about the case r cubed, it wouldn't make any difference if we were talking about c cubed, well, that arbitrary vector is x times e1 plus y times e2 plus z times e3. That proves that e1, e2, e3 is a spanning sequence for r cubed, because we've shown that every vector in r cubed can be written as a linear combination of E1, E2 and E3. And again, the proof will be precisely the same for C cubed, and it will be completely analogous for any other value of n. So this is the standard basis, and it's very, very important. We use it very commonly. There is also a kind of standard basis for the vector space consisting of all m by n matrices with real or complex entries. To describe that basis, we look at the matrix E subscript ij, which means the m by n matrix, with a 1 in position ij and zeros elsewhere. And then all such matrices, in some order, form a basis for the vector space of m by n matrices. For example, if we had m equals n equals 2, then these matrices Eij, as I and j range between 1 and 2, would be E1, 1 equals 1, 0, 0, 0. E1, 2 would be 0, 1, 0, 0. E2, 1 would be 0, 0, 1, 0. And E2, 2 would be 0, 0, 0, 1. You can prove that those things are a basis of M 2 by 2 of R if we're thinking of those as real matrices, or M 2 by 2 of C if we're thinking of them as complex numbers. And the proof will be exactly the same, at least exactly similar, to the proof we did for the standard basis of R to the n or C to the n. It's really, there's not a lot to check when you're showing that these things are a spanning set and you're showing that they are linearly independent. For example, those things are a spanning set of R of M 2 by 2 of R because any matrix A, B, C, D is equal to A times E1, 1 plus B times E1, 2 plus C times E2, 1 plus D times E2, 2. And that shows that the matrices E1, 1, E1, 2, E2, 1, E2, 2 are a spanning sequence for M 2 by 2 of R. And you can do linear independence in a very similar way. Let's move on to some more example bases. So we'll look at vector spaces of polynomials of a bounded degree. So here, at the top here, is the vector space of all polynomials in one variable x with degree less than or equal to 3 and with complex coefficients. So you'll remember that the definition of this was it consisted of all things of the form a0 plus a1x plus a2x squared plus a3x cubed, where a0, a1, a2, a3 are complex numbers. And this has as a basis 1x, x squared and x cubed. And the reason for that is it's clearly a spanning set, because you can see from the definition of this vector space that every element in the vector space is a linear combination of 1x, x squared and x cubed. And on the other hand, for polynomials you're allowed to compare coefficients. For complex or real polynomials you can compare coefficients. So if a plus bx plus cx squared plus dx cubed is equal to the 0 polynomial, then for polynomials we can compare coefficients. To get a equals b equals c equals d equals 0. So that proves linear independence. We already talked about being a spanning set, so these elements 1x, x squared, x cubed form a linearly independent spanning set for this vector space, and so they're a basis for this vector space. So let's now think of a slightly harder problem to do with finding a spanning set for a different vector space. So we're going to look at the vector space S, written here, which consists of all matrices A, B, C, D in M2 by 2 of R with the property A plus D equals 0. And the question is, how can we find a basis for S? So I promise you that that thing really is a vector space. It's genuinely a subspace of M2×2 of R, and therefore a vector space in its own right, with the usual matrix scalar multiplication and the usual matrix addition. That's the thing you ought to check. So you should check that S genuinely is a subspace of M2×2 of R. But let's say we wanted a basis for this. So how could we find one? So a basis, remember, consists of a sequence of elements of S. So they really must be elements of S, which are linearly independent and which are a spanning sequence. So to help us find such a sequence, it helps us to write out an expression for an arbitrary element of S, perhaps in a slightly different way, because we know that A plus D must be 0, so one of the variables here is redundant. You could rewrite D as minus A. So let's do that. Any element of S equals A, B, C minus A. So that's actually helpful to us here because it lets us write this arbitrary element of S as a linear combination of three things in S. So this equals A times 1, 0, 0 minus 1 plus B times 0, 1, 0, 0 plus C times 0, 0, 1, 0. And now notice that each of these three matrices are actually elements of S. So this matrix is in S because if you add the top left and the bottom right entries, you get 1 plus minus 1, which is 0. This matrix is also in S, because if you add the top left and the bottom right entries, you get 0 plus 0, which is 0. And similarly, this element is in S as well. So these things are all elements of S. Let's give them names. We'll call this one H, and this one E, and this one F. Now what this shows is that H and E and F are a spanning sequence for S. They're elements of S, as we just checked, and we've shown that any element of S is a linear combination of H and E and F. We found a spanning sequence. And in fact, this spanning sequence is a basis. So I'm going to leave it to you to do the proof that H and E and F are linearly independent. So this is a linearly independent Li for short sequence. And when you've done that, you will know that HEF is a spanning sequence and linearly independent, so it is a basis of or for S. Okay, so there's a nice non-trivial example of a basis. So here's one of the useful properties that bases have. If you have a basis V1 up to Vn of a vector space V, then every element of V can be written uniquely, so in one way and in only one way, as a linear combination of V1 up to Vn. Before we talk about why this is useful and what it's telling us about the meaning of a basis, let's just do a quick proof. First of all, we know that every element of V is equal to a linear combination of V1 up to Vn, because a basis is, in particular, a spanning sequence. So every element must be writable as a linear combination of V1 up to Vn. So given any element of V, it's certainly possible to write it as a linear combination of V1 up to Vn. And the question is only, is there more than one different way to write some particular V as a linear combination of V1 up to Vn? So let's suppose we had two linear combinations which were equal to one another. So two linear combinations of V1 up to Vn which were equal to one another. And we need to prove then actually the coefficients in those linear combinations are equal, they're all the same. So we'll take two linear combinations, which I can write like this and like this, and we're going to prove that actually if those two things are equal, then A1 must be equal to B1, and A2 must be equal to B2, and A3 must be equal to B3, and so on. And again, this just comes from doing manipulations to those sums or linear combinations of vectors, which we're allowed to do because they follow from the vector space axioms. So if you have that equality, then you can subtract the right-hand side from the left-hand side, and you can collect coefficients of v1 and v2 and v3 and so on. And when you do that, on the right-hand side you'll get the 0 vector, and on the left-hand side you will get the sum of ai minus bi times vi. But these v's are supposed to be linearly independent. The only linear combination of v1 up to vn, which is equal to the 0 vector, is the linear combination in which all coefficients are 0. So the linear independence of v1 up to vn, which comes from the fact that they're a basis, tells us that actually all the coefficients in this linear combination are 0, and therefore ai minus bi is equal to 0 for all I. In other words, ai is equal to bi for all I. And that gives us the uniqueness that we claimed. So what this allows us to do is to generalize this idea of comparing coefficients, which I talked about for polynomials. If you have two expressions, two linear combinations of basis vectors, then the coefficients of a given basis element must be the same on both sides of this equality. So if a linear combination a1v1 plus a2v2 and so on is equal to another linear combination b1v1 plus b2v2 and so on, then actually you can compare the coefficients, and those coefficients must be equal. So when v1 up to vn is a basis, that's what you can do. So this is telling you that when you have a basis for a vector space, you can use that as a kind of system of coordinates for elements of that vector space. What I'm talking about here is easiest understood if we think about a simple example like r squared. So if you have elements of r squared, like x, y, then sometimes people say x and y are the coordinates of that vector. And what x and y are in terms of bases is that they are the coefficients of this element of the vector space r squared in terms of the standard basis. And whenever you have a basis for a vector space, you can write every element in this vector space uniquely as a linear combination of those basis elements. So the coefficients, when you do that, are like the coordinates with respect to that basis. So let's finally look at a little bit of motivation for bases. I mean, for vector spaces like the space of all n by m matrices, or the vector space of height m column vectors, we already know some standard bases. So why would we care about having multiple bases? Like, we've seen that the same vector space might have lots of different bases, infinitely many different bases, in fact. So why would we care about having more than one basis for the same vector space? Well, the answer is that different bases can give you a different way of looking at the same vector space, which can tell you different things about the elements of that vector space. So we're going to look at an example which is to do with images. So let's say you were working for some artificial intelligence startup which is interested in image processing. It's interested in understanding images. Here are, on the left-hand side of this slide, the simplest images I can possibly draw. So the images consist of two squares, 2 pixels if you like, and those images are black and white. So they might be, each square is somewhere between a black square and a white square, so any shade of grey between black and white. So one of the nice things about vector spaces is that you can use them for representing data like this. So you could represent an image like this by using a number to tell you how dark the first pixel is, and a number to tell you how dark the second pixel is. So we might use very negative numbers to represent dark pixels and very positive numbers to represent light pixels. For example, we might represent this one as the first pixel is very dark, so perhaps it's -1000, and the second pixel is very light, so we might give this some very positive number, so 1500. And we might represent the next one. Well, here we've got two very bright images, so these will be both two very positive numbers, like this. And the next one will be something like, well, you've got a very bright first pixel and a very dark second pixel. And the last one, well, you've got a fairly dark number, a fairly dark pixel at the start, so maybe this is some number in the middle, and the second one is also very dark, so maybe -100,000 again. So in this way, we can represent our images as elements of R². So in my table here, I've got an image, and here I've got an element of R². So when we write one of these vectors like this, we can write them in terms of the standard basis. So for example, this first image here, that would be corresponding to the vector, which is -1000 E1, first standard basis vector, plus 1500 E2. And the coefficients of the standard basis vectors have a concrete meaning. The coefficient of the first standard basis vector is telling you how dark the first pixel was, or how light the first pixel was. And the coefficient of the second standard basis vector is telling you how dark or how bright the second pixel was. So what happens if we start writing an arbitrary vector in terms of some different bases? So if we have an arbitrary vector in R², which corresponds to some image, one of our 2 pixel black and white images, this is x times E1 plus y times E2. And the x and the y here are telling you exactly how bright and dark the first pixel and the second pixel are. But we could also rewrite this in terms of another basis of R². So you'll remember that we know another basis, which was f1 equal to 1, 1, and f2 equal to 1 minus 1. And what we saw was that a vector like xy was equal to x plus y over 2 times f1 plus x minus y over 2 f2. And now you see that these numbers, x plus y over 2 and x minus y over 2, really have a different meaning and a concrete meaning in terms of images, because this one is the average brightness of the 2 pixels. That's how bright the image is overall. So we could think of this as the overall brightness. So the average brightness of the image. And the second one also has a meaning. X minus y over 2 is how different the 2 pixels are. Or rather, to be more precise, it tells you how much brighter the first pixel is than the second pixel. So the expression for this image in terms of the second basis is in fact giving us a second equivalent description of the same image. It's telling us how to look at these images in a different way. So we can either look at them by describing them by saying how bright the first pixel and how bright the second pixel is, or if we represent them in terms of the second basis, we can describe the images by giving the overall brightness and giving the difference between the 2 pixels. So these 2 bases for this vector space gives us 2 different ways to look at the same data. And both ways of representing the data might be useful to us in different ways.